Question 26. Provide a circuit which implements a half-adder, inputs A, B, and output S and Cout, using only 2-to-1 multiplexer. For full credit, you must use it as few multiplexer as possible. And we can derive the truth table of half-adder A, B, C, and S. And the function is A plus B. If there are any carry output, and then we must write 1 for the carry, as the sum is the least significant bit. Next, we can use K-map to derive the Boolean function of sum and carry, and we found that S is A exclusive or B, and C is A and B. Now let's consider the output S. As I mentioned, S is A exclusive or B, so if we choose A as the enable bit, if we choose A, then we must not choose B. So the multiplexer for sum at the 1 place, we have to write B plum. That is to say, if we choose A, then we must not choose B. So, namely A and B plum. Otherwise, if we does not choose A, we have to choose B instead. So we put B at the 0 place. So to sum up, the output S for the multiplexer 2-to-1 is that if we choose A, then we must not choose B. So then we put B plum at the place 1. And if we don't choose A, we choose B instead. So B is at 0 place. Now let's consider the output C. As we mentioned, C is A and B. And if we choose A as the enable bit, if we choose A, then we must choose B. So if B must be placed at place 1. And if we don't choose A, then we don't have to choose anything. So the 0 place at the multiplexer C is 0. We can just write 0 for the 0 place. In other words, we just have to use A as the enable bit and B for the place 1. Now, let's combine the 2 output and the 2 multiplexer. We can use A as the enable bit, so we connect A to the multiplexer of carry and sum, and we use an inverter for the B input for the sum multiplexer at place 1, and B connected to the carry multiplexer of place 1 and the sum multiplexer of 0. And for the last input of multiplexer C, we just have to write 0 for the 0 place. That is the whole answer for question 26. Thank you.